So if we go to our little local maximum and try to zoom in, the question is, will it begin to resemble a straight line at that maximum also, do you think, or no? Because that's the point that doesn't look, clearly doesn't look like a straight line, whereas parts of the function already do almost look like a straight line. You guys think it'll become like a straight line there at the maximum or no?
You zoomed really, really close.
If I zoomed in really, really close, well, let's find out. Oh, I hit the home button, not the zoom in button. All right, does it look any different?
Nope.
Nope. How about now? Not really.
Really.
Yeah, not really. How about now? Still not really, right? How about now? Not really. What about now?
No.
Yeah, maybe not. Now I'm saying maybe it's starting to flatten out, isn't it? On this short little interval that I'm looking at, right? Where each of the, these 4 little marks here is 200ths. Starting to flatten out, isn't it? Still flattening out, flattening out, flattening out. Does it look like a straight line yet? No, not quite, but pretty close, doesn't it? I mean, it's still going up and it's still coming back down, right? What about now? Yeah, you can still see it's coming up a little, coming down. But if we keep zooming in, eventually, right there at that local maximum, even at the local maximum, it pretty much begins to look like a straight line. Would you guys agree?
Yes.
Yeah, and that's what we call linearization. And that's the whole, well, not the whole idea, but it's one of the big important ideas about derivatives and tangent lines, is that the derivative gives you the tangent line slope. And if you draw the tangent line of a function, then the function will begin to resemble that on a very small interval surrounding any x value that you choose where that derivative exists. That's called linearization. So we're going to use that idea that the tangent line looks at a function. Something happened with my mic. Can you guys still hear me?
Yes, we can hear you.
It's gone off of my Bluetooth, off of my headphones. Let me try and fix this problem here. Sorry. Hear me now? Still?
Yeah.
All right, perfect. Okay, so we're going to use this idea that the function begins to resemble a straight line, and in fact, the straight line that it begins to resemble is its tangent line at that point, at any point where its derivative is, to approximate the value of certain functions at values very close to a value that we might know. And that sounds a little bit weird, I think, to start with, but that's what we're going to do. And we're going to take a look at a function. We're going to start with this function that is, we'll start with the function on the next page, but we're going to start with the function the square root of 1 plus x. But before we can do that, what we need to do is we need to figure out a generic equation for the tangent line at any point. So if the point that we are going to use is the point a comma f of a, if that's the point we're interested in, then what's the tangent line at that point? Well, it should be y minus f of a equals the slope, so f prime of a times x minus a. Would you all agree with that? Hopefully. That's just point slope form, right? Y minus y1 equals m times x minus x1. Good or no?
Good.
Okay. And so this line, which is just the tangent line at x equals a, is called the linearization. And if we wanted to find the y value of some function f of x, we could just add the f of a over, which would give us y equals f of a plus f prime of a times x minus a. And that function we call the linearization function. And that linearization function will give you a very, very good estimate for the value of, let's say, the square root of 101. Right? It's a value close to the square root of 100, which we know. And so we'll use the tangent line at the square root of, or at, the tangent line at 10 to figure out what the square root of 101 is. Does that kind of make sense, the idea we're going to use? Or to get an approximation of it? It's a very good approximation. Make sense or no?
Yes.
All right, cool. So here's that linearization function. L of x is what we call it, capital L of x. Capital L of x is equal to f of a plus f prime of a times x minus a. It's what we just did on the other page with the with the point slope form. So what we need to do for any particular function that we might use is we need to figure out what's called a center of approximation. And the center of approximation is the value of x that I can plug into my function that I know that value already. So what we're going to do is we're going to try to use the function square root of 1 plus x to approximate the square root of 1.02. So what's a value that's very close to 1.02 that I know the square root of?
1.
1, right? 1 is very close to 1.02. I know the square root of 1. What x value should I use in the square root of 1 plus x to give me that value of 1 inside the square root that I know?
0.
Should be 0, right? Because the square root of 1 plus 0 gives me the square root of 1. So this, we're going to say a equals 0, and this is our center of approximation. And that's the a value in our linearization equation up here. So everywhere we see an a, we're going to replace it with 0 up there. What's the x value that I need to have in my function? What am I looking for? I'm looking for f of what value?
.02.
Right, I'm looking for f of 0.02, which tells me that x equals 0.02 when I plug it into this equation up here. So those are the two important things you need to find. Well, two of the important things you need to find. The center of approximation, so the a value that makes your function very close to what you want it to be, and the x value that makes your function exactly what you want it to be. And then we also have an f prime piece in here. So we're going to need to figure out what f prime of x is. So what's f prime of x? Should be 1 over 2 root 1 plus x times the derivative of 1 plus x, which is just 1. Everybody good with all three of those important pieces that we're about to use?
Yes.
Spectacular. Okay. So let's plug it all in. We want f of 0.02. F of 0.02 ought to be approximately equal to L of 0.02, which should equal f of a, so the square root of 1 plus 0, plus f prime of a, which is 1 over 2 root 1 plus 0, times our x value, 0.02, minus our a value of 0. Everybody good with that so far? Any questions or issues on that? All right, so let's evaluate. What's the square root of 1 plus 0? It's just 1 plus, this is 1/2 of 0.02. And what does that come out to be? That's just 1.01. And you may look at that and be like, wow, great. If somebody asked me to guess the square root of 1.02, I'd probably just say something that sounds ridiculous, like, I don't know, it's probably 1.01 or something like that, right? It doesn't seem like that's really that great of an approximation, but let's see how good that approximation actually is, because it's actually quite good. We can go in and we can take a look at the actual square root of 1.02. And what does it come out to be? It's 1.00995. So if I had an extra 5 here, that'd round up to 1.01. So it's only off by, looks like 500 thousandths is all that approximation is off by, which is a pretty darn good approximation. Wouldn't you guys agree? No, you guys wouldn't agree? You guys still alive?
Yes, it's a good approximation.
Oh, great. Okay. All right. Yeah, it's a good approximation. So we're going to see if we can do this with a bunch of other functions. So let's try this with the cosine function, where we want to approximate the cosine of 1.75. So 1.75 is pretty close to pi over 2. That's why I've listed pi over 2 as a value there. So we've got our function cosine x. We're going to use pi over 2 as our center of approximation, because we know the cosine of pi over 2, right? Should know the cosine of pi over 2. And if we look at pi over 2, it's pretty close to 1.75. It's not great, but it's pretty darn close. It's probably the closest value that we actually know the cosine of to 1.75. Would you guys agree?
Yes.
Okay, so that's what we're going to do. We're going to use a equals pi over 2. We're going to use x equals 1.75. And we're going to use f of x equals cosine x, which means that f prime of x is equal to what?
Negative sine of x.
Negative sine of x. So we want the cosine of 1.75, which is equal to f of 1.75, which is approximately equal to L of 1.75. Everybody agree that that should be true? Cosine of 1.75 is f of 1.75, which is about equal to the linearization of it. Good or no?
Makes sense.
Good.
All right, so now what's L of 1.75? Well, it should be f of a, so that'd be cosine of our center of approximation, cosine of pi over 2, and then plus f prime of a, so plus the negative sine of pi over 2, times our x value, which is, sorry, our x value is not pi over 2. Our x value is 1.75 minus pi over 2, x minus a. Good or no?
Good.
All right. What's the cosine of pi over 2?
0.
Okay, the 0 minus the sine of pi over 2, which is
1.
1 times our 1.75 minus pi over 2. And if we distribute that minus 1 through, what do we have? We get pi over 2 minus 1.75. And that seems like a really stupid approximation again, doesn't it? Kind of like, oh yeah, that's what they'd put on there as like an answer on a multiple choice test to fool you, because it's got all the numbers in it, and somebody that doesn't know what they're doing will just choose that one, right? Or it might be like the answer that, you know, some really snide and sarcastic person would give you, like, oh, what's the cosine of 1.75? I don't know, pi over 2 minus 1.75, right? Sounds kind of stupid, but it's actually a very good approximation for the cosine of 1.75, as we should be able to see here. So pi over 2 minus 1.75 is that. And the cosine of 1.75 is equal to that. And so we can see that they're only off by about 1/1000th. from each other, which is pretty darn good, wouldn't you think?
Yes.
Yeah, seems good. So any questions on that one? All right, so here's what I'd like you to do. We're going to do this one together, but I want you to take a second and see if you can figure out the function and the x value and the a value. So it shouldn't take you more than 30 seconds to a minute. So see if you can figure out what the function, the x, and the a values are for this particular problem. All right, what's the function here? You guys all got the function here? Should be f of x is what?
Square root of x.
Square root of x seems like a good one. What is the x value that we're interested in? Well, obviously it's 26. And what's the a value where we're going to center our approximation, our value that's very close to 26 that we know the square root of?
25.
Should be 25. So root 26 is f of 26, which is approximately equal to L of 26, which is what? F of a, so root 25, plus f prime of a. Oh, right, we didn't write out what f prime of x is. What's f prime of x? 1 over 2 root x. So plus 1 over 2 root 25 times x minus a. Good or no?
Good.
Awesome. All right, so now we'll just simplify. This is 5 plus 1/10 of 1, or 5 and a tenth, 5.1. And again, it seems like a stupid approximation, like, oh yeah, square root of 26, I don't know, 5.1. But if we go look at it, I promise you, it's a good approximation. Right, 5.099, that's off by 1/1000th if you use 5.1 as the approximation. Any questions so far, or is everybody good? All right, we're going to do one more of these. Cube root of 128. So I want you guys to take, I don't know, 2 or 3 minutes and see if you can do this one on your own. So first off, what's f of x?
Cube root of x.
Cube root of x. And what is f prime of x?
One over 3 times cube root of x squared. Or 2 over 3. Or negative 2 over 3.
Yeah. I mean, you're right. Either way, you want to write it 1/3 x to the negative 2/3, or 1 over 3x to the 2/3, or 1 over 3 times x squared, the cube root of x squared, you know, however you want to write it. Any of those are fine. What's the x value should be 128, but what's the a value that you're going to use?
125.
125, since we know the cube root of that. So cube root of 128 should be equal to f of 128, which is approximately equal to L of 128, which is equal to f of a, so cube root of 125, plus f prime of a, so 1 over 3 times 125 to the 2/3 times x minus a. You guys all get that set up? So what's the cube root of 125? Should be 5. And then down here, this is plus 1 over 3 times the cube root of 125 is 5, squared is 25. And then this should be times 3. So we got 5 plus 1/25, which is 5.04. Is that what you all got?
Yes.
Perfect. All right. So if we go back in and take a look, we can see how good this approximation is. And 5.04, right? Looks like that's off by 4 10,000ths, less than 4 10,000ths, right? Everybody good with that?
Yes.
All right. So we've used this for some pretty, some simple calculations, like the cube root of 128 or the square root of 1.02 or cosine of 1.75. But it's not just good for evaluating approximations of, operations like cube roots and cosines and all of that. It can really be applied to any function. If we have a small change in the x value or in the independent variable, then we can calculate using this same idea what the change in the y value or the change in the dependent variable is. And when we do it with any function rather than just approximating a value, we call it a differential. And the way differentials work is we know that dy dx is equal to f prime of x, right? That's just like a known thing that these are both just notations for derivatives. True? Well, what we do is we treat the dy as its own separate variable, as a dependent variable, as a change in y. And we treat the dx as its own independent variable, as a change in x. Okay? And if we treat them as separate variables, one could multiply the dx over to the other side. And we could say that a change in y is effectively equivalent to the derivative of the function at the x value I started at. So we'll call this our starting x value, times however much our x value changes, our dx. Okay? And so this is called a differential when we do this. And we can use it to approximate a change in a function's value, and it uses the derivative or the slope of the tangent line, which is effectively like using a tangent line or a linearization approximation on any function. Does that sort of make sense?
Could you repeat that, please?
Sure. Which part? All of it or just?
The part about linearization.
Yeah, so effectively this is the same as a linearization because, a linearization is just using a tangent line, right? We found f of a and we found f prime of a and we found x minus a. And we used a linearization. We used the point slope formula for the tangent line, right? At some x value. Well, that's effectively what we're doing here. We're saying, all right, take a function at some x value that you're interested in and figure out what the slope of the tangent line is. If you take the slope of the tangent line and multiply it by how much your x value changed, that tells you how much your y value changes, right? You think about the slope, your original slope formula years and years ago, delta y over delta x, right? Change in y over change in x. Well, if you know what the slope is, that's our f prime, right? Then the slope times however much your x value changes should tell you how much your y value changes. And so what we're doing is we're using a derivative, and you're going to do this on a very small interval and say that this is a good enough approximation for most things for how much a function itself changes if the x value changes just a tiny little bit. Does that make sense?
Yes, thank you.
Yeah, no problem. So any other questions on that before we do this first one here? No? All right, cool. So here's our function, y equals x to the 5th plus 37x. We're saying that we're going to have a starting x value of 1, and it's going to change by 0.01. How much does the y value change? About how much does the y value change? Well, using a differential, what's the derivative of x to the 5th plus 37x? It's 5x to the 4th plus 37. So our dy should be that times dx. And we'll just plug in our 1 and our 0.01. And what do we get? 42 times 0.01 or 0.42. So what this is saying is if our function is x to the 5th plus 37x and our x value goes from 1 to 1.01, our y value should increase by about 0.42. Good or no?
So this is also an approximation, right?
This is also approximation. Yep. Anytime we're using a tangent line to talk about a curve, it's always an approximation. But on small scales, it's a very, very good approximation. And this idea, not something that we'll cover in this class, but this idea gets sort of translated, and what we do is we create a series out of these in like the second semester of calculus that gives us the exact values of these, but that's neither here nor there at the moment because we don't cover that in this class. So, but it does build on this to become something even more exact. Yeah. All right, let's look at another one. So we have the function y equals sine of 3x with x equal to pi, and we're going to have the x value get smaller this time by 0.02. So dy should equal the derivative of sine 3x, which hopefully at this point you can do the derivative of sine 3x in your head without having to write anything down. What is that derivative using the chain rule?
Three cosine of 3x.
3 cosine of 3x. And then we'll have a dx attached to the end of it. And so we just plug it in. dy, our small change in y, is equal to 3 cosine 3 pi times dx, which is 0.02. And what's the cosine of 3 pi? Well, we can subtract 2 pi from it. That's the cosine of pi. And the cosine of pi is what? Somebody tell me the cosine of pi. Oh, good. I was gonna about to lose my mind. Cosine of pi is -1, so this is 3 times -1. And oh, I forgot my negative on my 0.02. Negative 0.02. The negatives cancel out, and our y value goes up by about 0.06. Good or no? Any questions or issues with that? All right, let's take a look at another one. Now this one's a little bit different because we've got x plus y equals xy. We got x's and y's on both sides of it. So we have two options. One is we can treat it like an implicit equation. And when we take the derivative of the x, it's just dx. And when we take the derivative of the y, it's just dy. Or we can try to solve for y. And it doesn't matter. Either way, we'll come out with the same answer. Let's just do it as an implicit one, just for the example, because sometimes you won't be able to solve for y. So if I take the derivative of the x using a differential, it's just dx. And then the y becomes a dy. And then the x times y is still the product rule because it's still a product of two functions. So it's x derivative y plus y derivative x. And we're looking for the value of dy, so we'll solve for dy. So if I take the dx and move it to this side and the dy and move it to this side, I get dy times 1 minus x equals, and I can take the x out of the other, dx out of the other side, dx times y minus 1. Everybody good with that so far? And then we just divide. Any questions or problems with that?
Why would you evaluate it or approximate it when you can actually just do the differentiation? Like, is there any like real world application for it?
Yeah, I mean, it's just, okay, so a couple of things. One, differentiating it wouldn't give you an exact value. I mean, you'd have to actually plug in 2 and plug in 2.05. And so that is a lot more work for somebody to do. The biggest real world application of it is not, okay, it's not like what you would normally think of as a real world application, but this idea of differentials and tangent line approximations, when you plug in operations into a computer where a computer is trying to like calculate all sorts of these different values, and it's got, you know, suppose you're doing like some sort of online banking thing or something, and it's got to calculate exactly how much something changes if the stock market fluctuates a certain amount or something like that, with like tons of tiny little changes and tons, I mean, you know, millions of little calculations. If you can decrease that number of calculations by half, so rather than having to evaluate it at x and evaluate it at 2.05 and then evaluate the difference between them, you can have your computer, you know, say, all right, derivative, plug in, done. And it's going to be close enough for whatever, you know, whatever small, tiny scale you're looking at, then it's going to save your, you know, your calculating time in the, you know, you're just going to cut it in half, which is very useful for, you know, things that fluctuate quickly sometimes, like the stock market. That's not a real good example. It's also used, I mean, it's also used, but not with a great degree of importance on like simple things like, let's say, blowing up a balloon. You know, we'd think about, oh, how much does the radius increasing by a certain amount affect the volume of this balloon? But those calculations are so easy that it doesn't really matter, and there's so few calculations that the time difference isn't a big deal. But when you're talking about number of calculations and the scale of, you know, millions and billions of calculations, it saves time. That's not a great answer, but it's the answer. And the other reason that we would do this is because the AP test expects you to know it. Other than that, it's not, yeah, I mean, other than that, it's not real super useful in the real world these days, especially with like all of our ability to use calculators to do stuff. So sorry, not the greatest answer, but that's the way it is. So let's plug our things in. Our dx is 0.05. And let's see, we got 1 minus x, so 1 minus 2, and we got y minus 1. Well, I don't have a y value though, do I? How am I going to get a y value?
Do you use the original equation?
Yep, we're just going to go back and say, all right, 2 plus y equals 2y, or y equals 2. And what do we get here? We get if x changes by 0.05, y changes by 1 divided by -1, just makes this a negative 0.05. Good or no? All right, I know we're over time by a minute already, but I want to do one last problem real quick, and then then I'll let you all go. So sometimes they won't just give you a function, they'll give you something like this. This is more like what you might see on the AP test for a linearization or a differential problem. They're usually pretty easy like this one is. This would be like a multiple choice question. So suppose I have a circle and I increase its radius from 10 to 10.1 meters. I want to use this linearization idea, which is the same as this idea of differentials. It's just using a tangent line to approximate. So we're going to use that to estimate the increase in the circle's area. So we need to write an equation that gives us the area of a circle. What should that be?
Pi r squared.
Pi r squared. And we're just going to use the differential. So dA is the derivative of this, 2 pi r dr. And what is our original r value?
$10.
10. And what should the change in our r value be? If it's going from 10 to 10.1, the dr should be 0.1. So dA ought to equal 2 pi times r times dr. And what does that give us? That the change in the area ought to be 2 pi meters squared, approximately. Any questions on that one?